Sarah, what's up? We're going to continue on with this bonding stuff by talking about more ionic bond information, specifically lattice energy. Now, lattice is a fancy chemistry and sciencey word for like cube, okay? So, you might have noticed if you ever looked at a grain of salt, it looks like a little cube. Okay, and there's a reason for that. It's technically called a lattice. It's not a cube, okay? We are now in chemistry, so we call it a lattice. And the reason why lattice is the shape of an ionic compound is because of the charge and the strength of the attractive energies of the charges. Basically, it's like building blocks. I'm going to try to draw. I mean, it's not going to look good. I'm trying. Give me just a second here. Oh, I just drew this cube, and I'm really hoping this turns out all right. So, I try. It's like, you can draw a cube from geometry, but then at each vertex, each corner of the cube, you put either a sodium cation, positively charged ion, or a chlorine anion, negatively charged ion. And what happens is, all these bonds right here are ionic bonds. And imagine this copied across and down and really deep. You get like a big old cube, okay? Now, lattices are the shapes of ionic compounds, and you may wonder how much energy it takes to form a lattice, and you may not be curious about that, but you may want to be curious about that because that's kind of something that teachers like to ask about this stuff, and it's basically the energy to form it. Okay. Now, what it's helpful to know is this an endo or exothermic process? Because that's a very big concept in chemistry. Is a process taking heat in or giving heat out? Is heat entering the system, the situation, the lattice in this case, or is it exiting? So is it entering endothermic or exiting exothermic? A general rule about bonds is that when they form, you may think, I don't know how bonds really form. But it's better to think, hey, if bonds are to be broken, okay, that's when heat is doing the job to break bonds. Okay, think of ice, an ice cube, by the way, right? So if you're going to melt ice, if you're going to break bonds in an ice solid water state in order to form liquid water, you might want to pump some heat into that ice cube, okay? So that is an endothermic process. So when heat enters, bonds break. Therefore, if bonds are forming, think of it in reverse, heat must be exiting the system. So anytime a lattice is forming, that is an exothermic process. Keep that in mind. Okay, that's an important one. Now, you might be wondering, and again, this means it's code for like, hey, teachers will probably ask you this stuff. I wonder what would happen if it wasn't just sodium chloride. Let's think of some other things, other elements in sodium's column, in sodium's group. What do we have? We have lithium, we got sodium, we got potassium, and so on and so forth down the line. What do you think would be the strongest lattice of all of those? In other words, which would have the highest lattice energy? Which would have the highest amount of energy required to break it apart? If we wanted to break it apart, it being the cube, the either lithium chloride, sodium chloride, potassium chloride, they'd all kind of look like this shape. So where would you find the most strong lattice? Would it be with lithium chloride? Would it be with sodium chloride? Would it be with potassium chloride? Would it be something on the very, very bottom, row 7, which I forget off the top of my head because I'm not looking at the periodic table right now? Radium, maybe? Cesium? Maybe cesium? CS? I forget what's in the bottom left of the periodic table. That's bad of me. I should know that. But, pause this. Do you have any thoughts? What would be the strongest lattice? Which would be the weakest? And is there a trend? Because we talked about trends before too. Does it matter if you go down a group? Pause the video, think about it, and then hit play again, and I'll be rambling on about it. So take a pause. Okay, you're back. The idea is the smaller the cation, the tougher it is to break apart. And the reason is I'm going to write this down real quick. Real crappy drawing. I apologize for this. But what happens is, what do you think would fit together like a puzzle best? Something where the stuff's the same size, or where there's a kind of difference between the sizes of the molecules, or where there's like a really big difference between the size of the molecules. And you know what, in fact, even better than chloride, I'm going to do fluoride, because fluoride's on the top of group 7. It's on top of the halogens. Okay? So, this would be the smallest halogen right here. Because remember, in the upper right, we have the smallest atom sizes. So, check this out. Lithium fluoride, roughly the same size. They're both in the same period. Makes sense. Sodium, we go down a row. We go down a period. So, we are a little bit bigger. Okay? Sodium's bigger than lithium. I should have really made this huge, but potassium's be bigger than sodium. And therefore, you know, if you try to make a lattice, a cube structure with this, lithium fluoride, hey, should go like hand in hand. Same size, should fit together kind of like this. Okay, if I do sodium with fluoride, that is going to maybe look like a it's gonna look a little bit, you know, like big mixed with small rather than small mixed with small, and so on down the line. So higher lattice energies, remember the amount of energy required to form it or break it up, the higher energies are going to be here where it fits together better like a puzzle. Okay, so higher up on the periodic table, that's where you have more lattice energy. So keep that in mind. It's kind of like a weird thing to think about, but again, teachers probably be asking it, so you want to know. And because of that, this guy would have a very, very high melting point. You know, these are going to have high melting points, but not as high. The more nice the lattice looks, the more size close the two ions are, the cation and the anion, the more close in size they are to each other, the harder it's going to be to destroy this unit. Okay, you're going to need more energy to melt it or to break it apart. So those are some facts about what you're dealing with. Now, there are some other facts about the about lattice and stuff like that, but that's just a little intro for you. We'll get more into those later. What I want to do now is talk about ionic bonds with what are known as Lewis dot structures. It seems kind of different from lattice, and it is in a way, like the structure of a lattice itself and the just the energies involved. But it still deals with ionic bonds. That's the arching umbrella kind of a topic. So it helps to know what these things even are. So Lewis dot structures. I remember back when I was learning these things, they were not necessarily fun. They were pretty annoying, I'm not gonna lie, But where I was annoyed, you will not be annoyed, because I am going to try and diffuse every little annoying booby trap around these things. Okay, first of all, Lewis dot structures. Now, Lewis was a chemistry guy. Go figure, we're talking about chemistry, and this guy's named Lewis, and he came up with this. So, he also came up with a system of acids and bases, which are really, really good, but we're not going to talk about those now. We're going to talk about the Lewis dot structures. So what Lewis dot structures are is basically you're going to take an ionic or a covalent compound, okay, more than one atom, and you're going to represent it in terms of its valence electrons. Now, maybe in an old video you remember, maybe you've been reviewing a lot by the time you've watched this video, and so you know exactly what valence electrons are. If you do not remember what valence electrons are, they are just the electrons in the outermost energy level. Okay? And I wrote it down for you. Look at that. Valence E minus, which is a lazy way of me writing or abbreviating electrons, even though I wrote electrons right after it, which makes no sense. But anyway, electrons in the outermost energy level of an atom. So remember, sodium, for example, its atomic number is 11. Okay, it has 11 total electrons. That does not mean it's got 11 electrons in its outermost energy level, because remember the 2-8-8 rule. And if you don't, we'll talk about that. But I think I mentioned it in a previous video. So sodium has 8 electrons in its second energy level, total of 11. 2 in its first, I forgot about those. 2 in the closest energy level to the nucleus, 8 more in the next energy level out, and in the third energy level, it's only got 1, because it only has 11 total. 2 in the first, 8 in the second. We have 11 total. 11 minus 8 minus 2 is 1, so 1 valence electron. Remember, going from left to right, those 8 main columns, we're not counting the transition metals now, that group in the middle. Group 1 has always got 1 valence electron. Right next to it, the alkaline earth metals, 2 valence electrons. Jump over the transition metals. Boron's group 13. It's got 3 valence electrons. Carbon's group has 4, nitrogen's has 5, oxygen's has 6, fluorine's has 7, and helium's has 8. Because they all have 8, they are called the inert gases. They're noble gases. They don't react much, if at all, because they are satisfying the octet rule. They already have 8 in their outermost energy level, except for helium, because it's so small it only has 1 energy level, and it's got full with 2 valence electrons. So instantly you should be able to tell, for example, that if I say, hey Sarah, how many valence electrons does sodium have? You would say, oh, it's got an atomic number of 11, even whatever its atomic number is, it's on the far left of the periodic table. It's in that first column, so they all have 1 valence electron. So I'll do it like this. Sodium, natrium, by the way, that's a Latin name, that's why it's called Na, has exactly 1 valence electron, so a Lewis dot structure would look a little something like this. That one single dot right there above the Na shows me that it has 1 valence electron. Now, believe it or not, I never knew this when I was your age, but there are actual ways of placing the dots. Like, is this fully correct? I don't know. I haven't studied enough. I'm not being honest with you, but I don't think your class is going to get into it that much. Usually what you want to do is you do want to put a dot, think of it like a compass, like north, and then east, and then south, and then west, and then double up. I don't think the real way does that. I think it goes like 1, 2, 3, 4, 5, 6, 7. It's some weird pattern. It doesn't follow the same, like, just clockwise or counterclockwise pattern for whatever reason. But again, I don't think your class is getting too in depth with that, so just get the basics for right now. So sodium would look like that. Lithium, by the way, would look exactly the same because it's right above sodium on the left-hand column, so it's going to have one valence electron as well. So lithium would look just like that. Okay? Now, our favorite, sodium chloride. Chlorine has 7 valence electrons. Remember, it's a halogen. It's in group 7 right next to the noble gases. So those guys have 7 valence electrons. They just want to gain 1. Or lose 7 to make sure that their outermost energy level is complete with 8. What do you think is easier, gaining 1 or losing 7? I would lie on the side of gaining 1, and that's what chlorine and fluorine and bromine and all those guys want to do. So I would say that chlorine look a little something like this. Check it out. 2 on top, 2 on the left, 2 on the bottom, 1 on the right. Could it just be 1 on the bottom and have 2 left, 2 right, 2 top? Yeah, as far as I'm concerned. I think as far as your class is concerned, the answer is yes. And if your teacher cares, your teacher will let you know about where the dots go. Now, being that the octet rule is key and that every one of these elements really wants 8 electrons in their outermost energy level, doesn't this electron seem like it would be a perfect fit right there? So then sodium would have literally none in its outermost energy level, but then you go to the next closest one to the nucleus, it'll have 8. But we don't represent that. We just say, okay, now sodium would have none. Because what happens is sodium wants to get rid of its 1 or gain 7. Chlorine wants to gain 1 or get rid of its 7. It's just less work to deal with the 1 electron rather than 7 electrons. So sodium's lone electron goes right there. Okay? So that's what happens. And then you get an ionic compound, because remember, in ionic compounds, electrons are donated. Okay? So what we end up with is NaCl, which overall is electrically neutral, even though it's 1 ion here and 1 ion here. Once that 1 electron, remember, is given, donated to the anion, it is a neutral molecule at that point. So here's what we would get. Okay, that's really what we have, okay, with the Lewis dot structures for this stuff. Okay, we got sodium, it lost, technically it donated its 1 electron, but in and of itself, it started out with 11 electrons, now it's only got 10 because it's the outermost one it gave away. So you put brackets around it, no dots, because again, in its outermost, the 3rd energy level, because it's in the 3rd row of the periodic table, it's got no electrons, so we don't have any dots around it. And then chlorine did have 7, and its 1 extra came from sodium, right there. And so I put it in brackets. It's happy with 8 electrons, and it gets a minus charge because it should have 17 electrons, but in its outermost energy level, it had 7, now it's got 8, so it's happy. Okay? So that's just one example of valence electrons, what's going on behind the scenes, and how you get Lewis dot structures with those. Now, Lewis dot structures get crazy, okay? They get very, very, very intimidatingly crazy the nastier you get. And the ionic ones aren't that nasty, I'll tell you that. The covalent ones are nasty because sometimes electrons, actually always, electrons in covalent bonds are shared, okay? They're shared. So next video, I'm going to talk about what's up with covalent Lewis dot structures. But remember, Lewis dot structures, you only care about valence electrons. You don't care about the closest ones. You're either going to have 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, 6 dots, 7 dots, or 8 dots. Unless you got no dots, like you do here. But that's because, again, sodium gave its 1 to chlorine. Okay? So, again, this is just a little companion for what you're studying, and I'll get you some good advice for covalent bonding coming up, and I'll give you some more ionic bonding examples as well. But for now, just want you to get comfortable with the idea, not only of lattices, what they are, lattice energies, but also starting to get into Lewis dot structures. Okay, Lewis, named after the guy who does this stuff and who created it. Dots, because electrons are represented by dots, and structures because, well, how do these things look, and how can we represent those so they make sense to us? So hopefully this kind of makes sense, and if it doesn't, just rewatch the part again about the Lewis dot structures to hopefully have it make sense. Just like reading a textbook. First time is going to be weird. Every single time you check it out after that, it's going to make more and more and more sense. So hope you're feeling well, better than you have been, and keep staying tuned for more videos.